You know, it's funny because everything in math just basically simplifies down to addition. So it's pretty important that we're good at that. So let's take a look at what's called sigma notation. Sigma notation. And what this means is you're just adding up a whole bunch of different numbers. It's represented like this. I equals 1 to some number n, and then we put ai right here. All right. And what that means is, let's say a1 plus a2 plus a all the way to some number n. You're just adding up a whole bunch of numbers. All right. Well, let's say we wanted to add up numbers in a row. We start with the sigma notation of I equals 1 to some number, and then I, and then that would basically equal 1 plus 2 plus 3 all the way to whatever number you decide. And this gets simplified down to n times n plus 1 divided by 2. You just plug in n and you get that answer. It's going to be pretty easy. You'd also do this if you were to say to n of I to the third power, okay, not squared but to the third power, then you square everything here. So n plus 1 squared divided by 4. It's kind of funny how this works. All right, and then there's one more. If you're going to square the i's, then it would actually just be, remember that this is sigma, I equals 1 all the way to n, and then this would be n plus 1, 2n plus 1 divided by 6. All right, so that's if you're trying to add up, you know, either just one number all the way, or, you know, if you're squaring each number, or if you're cubing each number. Well, let's say we wanted to approximate an area under this curve. It's going to go from point A to point B. And as you can see, it kind of makes this little shape right here. This is not a very good shape to make. So I'm going to try to divide this up into little boxes, you know, from here. And there's two ways that we can do this. Usually, you know, this way is kind of the nicer way. If you go from the right endpoint, it's a little bit nicer than if you go from the left. If you make sure that the right side of this box touches, it's a little bit nicer for the equation. We'll see later. But I'm going to divide this little thing into, I'm going to say 1, 2, 3, 4, 5. This is n equals 5 boxes, right? This would be another box, another box. It's not going to be quite the exact area, but it's an approximation. So we're going to approximate this area by making 5 little boxes that will sort of shrink in size. Obviously, it's going to be bigger here. Well, it'll become different sizes over there. We could say that this point right here is x, xi. Mark that like this, because this would be I number 1, 2, 3. This would be like the third I or something, so xi. And then this right over here would be another, this would be like x and then I minus 1, okay? Because obviously that would be, you know, that would probably be x2, and this would be x3. So if we are trying to calculate that, we would want to have these coordinate points, right? So let's head over to the actual formula, and it would be something like this. AL, if we're approximating from the left side, if this side was touching there, it would look something like this. The math wouldn't be so nice, because we would start with I equals 0 on this little sigma thing. Start with I equals 0, and you go to n. So however many you choose, in this case it's 5. And then here, you'd say f, x, and then you can say I minus 1. So start making things kind of complicated here. And then you're going to use this delta x concept. Well, we'll figure out what delta x is in just a second. And now if we're going to look at it from the right endpoint, which is what I actually did draw right over here, where this point of the box is touching on the right, then it looks a little bit easier, because you would start at I equals 1 here, and you would go to n. Instead of 0, it's 1 on this side, and then you'll have your f of x, f of x. I mean, I guess that should have been in blue, the f of x, you know, but whatever. And then over here, this would be I, and then you would have delta x over here again. So it's just a little bit simpler, because you don't have to deal with I minus 1s and dealing with that. You can just simply put I and you'll get your answers here for approximating. So let's figure out what xi is, xi or xi minus 1, whatever it is. Let's figure that out real quick. So we would have x, and then here's an I. That's going to be equal to our original A over here, this first A point, A, plus I, so whatever I you're at, let's say you're at your first I, your second I, whatever, it doesn't matter, whatever I you're at, and then you have delta x. We got to figure out what delta x is, so delta x is going to be equal to b minus a over n. Okay, so b minus a over n. All right, and now we've got this sort of delta x. Delta x is essentially the size of this, right? b minus a divided by 5 will give you the size of this little thing right here. And that's the delta. That's essentially, you know, you're sort of sticking in between here. So you got your I and your delta x. So that's quite interesting. So this distance that's right here, xi minus xi minus 1, that distance is delta x. And I'll try to write that right here. Xi minus xi minus 1, that distance between those 2 points is delta x. That's what delta x equals right here, equals delta x, that little distance. And then, you know, whatever the height is, we're going to have to sort of figure out based off of, you know, plug it into this whole equation and stuff like that. But we're going to have this little xi that we can use, and we get to using delta x, and the i's that we have to follow along with the i's. So we start doing all that. So let's solve this. Let's try to figure this out. We'll start with the left side. We'll go ln equals fx, and the first one is going to be 0, x0. So if it's x0, then we take a look at xi, and we're going to go a plus 0 delta x. So it's just a. That's going to be our first term, right? A is this little thing, and then times delta x. That's going to be our first little piece of this puzzle. Then you can start adding on the next one. So f, you know, f of x1, f of x2, all that stuff, until you're going to arrive to, at some point, f of x, and then n minus 1. You want to finish at n minus 1, not at n on this one. And then you're going to end this with the delta x. You should be able to perform this calculation and get an answer for the lower estimate, the left-hand estimate. This is essentially the lower estimate on the left side. Okay? And for the right side, it would be this. Rn equals, a little bit easier, but we'll start with x1 this time. So I is 1. So that means that when you plug this into your equation over here, a plus 1 delta x. So now you start actually multiplying on your first one. It's not just going to be a, it's just going to be a plus, you know, you got to do the calculation there. And put the delta x here. And then, of course, you're going to do the exact same thing. Continue this forward until you get over here, fx, and this one ends on the n. So it's a little bit easier because you can just plug in, you know, the normal numbers here without having to do a minus 1 and everything. So it's nicer to get the right-hand estimate. This is the upper estimate on the right. So this is how you can estimate the areas under this curve. But let's say you actually wanted to get the actual answer to really properly get the area. What you'd want to do is take this n over here, and you want to set that equal to basically infinity. So as n starts getting bigger and bigger towards infinity, then that size of this gap will shrink so small that, like, you're going to get the exact area because you're following points instead of following a box, which will have error. You're following just points. So you can actually build, like, you can find the area of just a line, and then just multiply all the lines up, which is really weird, I know, but yeah, you're just finding the area of a line instead of using these boxes, and so that way it's exactly correct. So you just send n to infinity, and you'll get the answer there. Well, when we send n to infinity, that's called a definite integral. So definite integral. Let's go ahead and write that out in proper notation. Well, we'd say a to b fx dx. That's essentially what we're doing, is we're just sending this n to infinity now. So that's going to equal the limit as n goes to infinity. This thing becomes so big that this tiny little thing becomes a line, and we just go ahead and sum it up over here. So I equals 1 to the n. This is going to be f of x I and delta x. Perfect. So this is just going from 1 to infinity. That's kind of what we use in our calculations here, and that is the proper notation for this. Interesting. That's the definite integral. Now, if we didn't have any boundaries and we just went a straight up, all the way across everything, the entire function, then that would be called the indefinite integral. And we could say that over here, indefinite integral. We're going to look at things like the power rule. Let's say we have something like this: x to the n equals x to the n plus 1 divided by n plus 1. This is the power rule for indefinite integrals, and it's really important. This will solve any kind of integral that's x to the n power. You're just going to x to the n divided by n minus 1. The next one is going to be k dx. Let's say that's just a constant, and then it's not a function, it's a constant. This should be constant times, it's going to be equal to constant times x. Well, let's say you had these two things flipped, and it was kind of the wrong side. Let's say you were trying to solve a definite integral, and you had b down there and a up there. You wanted to flip those things. Here's your f of x dx. What you could do is just say negative a to b fx dx. That's going to switch the a's and b's. You put the negative in front. That's a good rule. There's a couple more. Let's see. A to c. Okay, let's say you had an a to c. If you wanted to split that up, you could do something like this. You could translate it into a to b plus b to c. Now I'm cutting out the fx dx part because it's kind of redundant, but a to c, you can break that up and split that up into two different ones. You go a to b plus b to c, just in case you want to stick something in between. Now let's take a look at some of these graphs and see if we can sort of figure out if we were adding some areas together, what would happen. So we have this graph right here, which starts pretty big positive on this side. This would give you a big positive area. And then on this side of the graph, however, you would get sort of this negative area. It's a smaller negative area. We'll notate that as area 2 and this one as area 1. Well, let's say we wanted to find the net. That would be essentially net. That would be a1 minus a2, right? So you would take your a1 minus a2 and that would give you net. Okay, net just basically means what's left after you've taken the big stuff and you've taken a little bit away from it. What's left, that's the net, right? Okay, and then let's say you wanted total. So total is going to be a1 plus a2. Of course, these are absolute values that I'm assuming here. So a1 plus a2 would give you the total. These are pretty obvious. Okay, now on this side we have an odd function. So this is an odd function. And you'll notice that on this side, if I were to add these two areas together, this is all negative on this side, okay? But it's equally negative on that side as this side is positive. So if I were to add these two things together, basically by writing this, from negative a, that would be this negative a right here to a, negative a to a of f of x dx, that's just equal to 0. So for any odd function, if I'm just going from negative a to a, and trying to find integral, it's just 0. It's a quick shortcut. And over here on this one, we can also do this for even functions. If we're going just straight from the negative number, it's not going to be 0 though this time. So you'll see how instead of one side canceling the other out, now you've actually got two of the exact same areas. So instead of having to calculate a whole bunch of different things, the integrals will simplify when they go from 0. If it's not a, if the a is some number, then it becomes kind of complicated. You have to do two calculations essentially, but it'll simplify down to 0. So it's simple. It's simple if it's 0. 0 to a. Great. F of x dx. All right. So instead of being the equal to 0, we can use 0 to start here and go from 0 to a. Just calculate that, and yeah, it's just gonna become a little bit easier. So these are the ways that we can look at these functions. This is going to be for even and odd integrals across, specifically from negative a to a. So now we get to the fun stuff. It's the fundamental theorem of calculus. This is where things might start to make a little bit of sense, maybe. So in the books, they like to make it a little weird. They like to say things like this: 0 to the x, and it makes kind of a little bit no sense until you look at it the right way. So they'll say f to the x of f of t dt, and that makes no sense, right? Because this should just be f of x. What this is trying to say is that there is an integral or an antiderivative of like that. So if you take the integral, it's going to equal f of x, and they're claiming this. They're claiming that you can take the derivative of f of x over there, and that's just going to equal f of x, the normal f of x. But it's weird because, wait a minute, that's f of t, not f of x. Like, those should be the same, right? And because if you take the derivative of f of x, it should be f of x. That makes sense. Okay, great. But why is it f of t dt and not f of x? This is kind of confusing, right? Okay, well, let's try to draw it like this. Draw a little thing like this. And this is going to be f of t right here. Here's f of t. All right, and well, this is going to be the t-axis. That makes sense. This is y-axis, of course. But what we're doing here is we're basically going along, and we're putting a point here and calling this point x. And there we go. So here's point x. Now, if I were to put x into this equation, it would be f, like here, at that point right there, it would be f of putting x in for t, okay? Right? So that makes sense. That's the point f of x. And now it's basically asking us, okay, we've got this whole area under here. That's what f of x is equal to right here. F of x, right? This is what we're doing, a little calculation from over here. This is being a is actually equal to 0 in this particular case right here. So a equals 0. Nice. And so I mean, everything makes sense so far, right? But let me propose pushing this x closer this direction. If we start pushing this x this direction, what will sort of happen is x will basically just become 0, right? And that point will sort of become the same thing. Okay, but what we can say at that point is something like this. Not there, but if I do this, if I make a little box, it'll start to make sense, because I'll go from 0, and then the very first point that you'll see right there is going to be an x. But I'm going to say dx. It's a really small one. Remember, if things are really small, we can put a little dx. So that's the distance from here to there. It's the very first x. That thing has gotten so small, the very first thing it moves over is not this massive, like a million things. It's just the very first thing that moves over is just x. And then this whole thing is making an area for us. And the very first thing we're allowed to plug in at the very top here is f and then x. So the very first, smallest little, this is literally the size of a microscopic point. I've just blown it up very large here. And you get the base of the bottom here is dx, right? So this thing at the bottom is dx, and then this thing at on the height is f of x, because that's the first point that we were able to plug in there. And so what we can kind of say is this, that f of x times dx. That's the area of that little box, isn't it? F of x times dx, base times height. That's the area of that little tiny box. And then, of course, this will kind of keep growing. And as we do this, it'll grow from the point 0, where we started, to x. And so now we've sort of translated that top equation into this equation. So it would make sense that if we were to evaluate this using, this is another given thing from the Fundamental Theorem of Calculus. It's going to be the Fundamental Theorem of Calculus right here. A couple of laws that we're allowed to say. First of all, this one, and then this particular one that we're stating here. If I plug in an x there, then that's going to equate to fx. You have to, first you take the antiderivative of this function, and then you plug in the numbers that you have here. X goes in, and then you're going to subtract a 0 over here. This is just basically called the evaluation rule, I suppose. So this is the evaluation rule. This evaluation is basically how you would evaluate these things. You have your function, you plug in your x, you take your antiderivative, and you plug in your x minus 0, and then you'll see how, yeah, well, remember this from before? If we took away the 0 at that point, we're essentially saying that those two things are the same thing. And now this whole kind of thing makes sense, hopefully. Yeah, interesting. Now there's 3 cases you might encounter if you're going to start evaluating things using the Fundamental Theorem of Calculus. Now they're usually asking for some kind of derivative, so it's d over dx of, you're going to be given this kind of thing, 0 to x, and then f of t, you'll get some kind of weird f of t situation. It'll ask you, okay, so plug in that variable into that function and get the derivative of that, and well, the answer is supposed to be f of x. You just plug in x. It's like really easy. Okay, and then they'll ask you some other stuff like, okay, well, what's the derivative of, let's say we were going from 0 to x squared, and that's going to be f of t dt. Well, in this case, you're going to have to use the chain rule, okay, because it's x squared. If you were to take the derivative of x, it's just 1. So in this case, it doesn't really do anything. But if we were doing it over here, remember our chain rule situation? Let's use the chain rule here. So if we were to take the derivative of this, now that we've stuck it in there, we have to take the derivative of what we just manipulated, so it would be 2x on that side. And that's how we would deal with squares and stuff like that. Now let's say if you had 2 variables all of a sudden, and you were going from x to x squared, that's going to be equal to, remember what we had over there in case of that situation when we had the a to c situation? Well, you have the same type of thing. It's going to go x to 0 all of a sudden. You're going to add in a 0, let the 0 help you out here, and then 0 to x squared. Just toss in the extra 0 in there, break it apart, and you'll rewrite this. It would be written as 0 to x squared. Make sure to flip these signs, turn that into a negative, and then slightly rewrite this like this, minus 0 to x. Alright, and it would be integral from 0 to x squared minus 0 to x. I'm just removing the ft dt situation because, it's just a lot of stuff to write down. So just some interesting things that might happen with the Fundamental Theorem of Calculus. Alright, so now we got two theorems to look at. First one is the net change theorem. Now it's really similar to what we had over here, xi, and then a plus ix. You're kind of doing the same thing here, but with like the whole function. So you'll have like, you'll want to know, alright, well, what is the function at that point over there? It's going to be equal to the first piece of the function, right? The first function evaluated at a, it's going to be that one, and then plus, you have to integrate the whole thing. So a to b, and then take the change, that's f of x right there, f prime, and it's a little bit sloppy here. So f prime of x dx. So you're just going to start with the original function and then add the integral of all the change, and then that's going to be the final function. It's the net change theorem. It's kind of written mathematically, kind of a, as usual, math is just hard to understand. But anyway, the mean value theorem. We also have f of c would be equal to 1 over b minus a, and then times the integral of a to b fx dx. And what this really is trying to say is that there's going to be some number that's right in the middle here, f of c, that if I were to multiply the length and the width and that, and then just, I could basically turn this weird shape into a box, like into a rectangle, you know, if I really wanted to turn this thing into a nice shape that was an actual rectangle, you would get the mean value, the height that would just perfectly turn this into a rectangle. That's the mean value of that height, and that's f of c would be evaluated at that point. That would be the height at that point c. All right, that's the mean value theorem. It's kind of interesting. Now let's go through some quick trig integrals. We'll start with the cosine. Cosine x is going to equal to sine x. I didn't add in the dx just to make things a little bit easier in written here. We go sine x, integral of that would be negative cosine x. If we had secant squared x, the integral of that is tan x. It's the opposite of the derivatives, right? Okay, and then if we had secant tan, then that's going to integrate into secant x. If we have cosecant cotangent, that's going to integrate into negative cosecant x. If we have cosecant squared x, that's going to integrate into negative cotangent x. Sometimes I just cut out some of these things just to make it a little easier to see and read. All right, now on this side, we're going to go the integral. This is an interesting one. Square root of 1 minus x squared is going to be equal to arcsine of x. Great. Yeah, we want to set up a lot of these integrals. If we could somehow set up an equation to look like this, this is an easy one. 1 plus x squared. If you could set it up like that, it's just going to equal arctan x. You want to integrate that. Bam. These are some nice, easy setups. Now this one's a weird one. So square root x squared minus 1. Awesome. This is arcsecant of x. All right, there's a few more kind of harder ones. So let's look down here. We've got 1 divided by the square root of a squared minus u squared. That's going to equal arcsine of u divided by the absolute value of a. And then on this side, I might have 1 divided by a squared plus u squared. That's equal to 1 over a arctan u divided by a. And at the bottom here, we go further. So 1 divided by u times the square root of u squared plus a squared, or actually this is minus over here, equals 1 over the absolute value of a arcsecant. And this is the absolute value of u divided by a. Yeah, so Again, these are kind of some things you can probably set up, manipulate some variables around so that they can fit to your liking. So now we can play with some exponential integrals, the exponentials. That's going to be exponential. That'll be like integral of e to the x equals e to the x. And maybe, let's say you had a harder one, so it was more like b to the x, d to the x, which is a regular number instead of e. That would be equal to e to the x divided by ln of b. That would cancel out on that side, but if you had a normal one, it would look something like that. Then you would use the logarithmic. Exponential ones are really easy. Logarithmic integrals, these might be a little bit harder. So let's say we had 1 over x. That's going to be equal to the ln of the absolute value of x. Obviously, there should be some dx's on that one, but I didn't put it. Anyway, the next one is going to be the integral of ln of x. That's going to be equal to x times ln of x minus 1. Not 11, that's a parentheses. And then over here, we can go to the final one, which would be more complicated. Say you have a regular logarithm, b, here's x. That's going to be x over ln of b, and then ln x minus 1. Okay, just trying to make this a little bit neat. There we go. Exponential and logarithmic integrals, it's not too bad. And now for everybody's favorite integration technique, it's substitution. Substitution. But here's the thing. I'm going to show you guys not how to do substitution, but rather how not to do substitution. So here's the steps that you need to do substitution. The first one, if you're going to check to see if you can directly integrate it without having to do any substitution. That's what we're going to show you today. Or you could follow up and start actually doing the u-sub. If you can't do the direct substitution and this doesn't work, it's too hard, then you start using your u-sub, because now you might need that to help you. So then you'd want to set up the dx chain. That means, yeah, sometimes you have to do a dx chain, right? I'll show you what that means in just a second. And then number 4, you want to type in your new limits, because if you start messing around with the u's, you have to start setting the u limits. So let's look at the new limits. All right, so anyway, here's the 4 steps of substitution. Let's say this though. Let's say you were trying to integrate something and you saw the derivative of the equation being multiplied like over here. So here's f of x inside like a square root, or this is like a sine or something, or you know, or power. But if you see like a square root, and here's the function, and you notice, wait a minute, that's a derivative right there on the left. Well, it turns out that you don't really have to do any kind of substitution. You can do a direct substitution, a direct integration with the system. So let's say you were given, here's an x squared, and then you're going to want to integrate that, oops, not equals, but x squared, and then here is x to the 3rd plus 1. And we want to integrate that. Now, you probably be thinking, God, I'm going to have to do some sort of substitution for this, or some rearrangement, and then, you know, I can do some foiling and rewriting. But I could easily integrate this by, I guess I could rewrite this quickly, real quick, just to make it a little bit easier to integrate, because we know we always want to do 1/2. If we want to see if we have a square root sign, I'm going to change it to 1/2. And then here, we can just direct, we don't even have to do anything here. I'll write this on the next line. So first I'm going to write x squared and then x to the 3rd plus 1. But then I'm going to directly integrate this by adding 2 to the top, so 3 over 2. And then I'll multiply the top and bottom by 2 divided by 3. And then I'm also going to take the derivative of what's inside of here. So times 3x squared plus nothing, obviously. So that's what's going to be multiplied down there at the bottom. these two things will cancel, and I'm going to be left with 2/3 times 3. So delete this, turn it into a 9 down here. This is gone from the top, so we're just left with 2 on top. And there we go. We are done. So we didn't have to do anything except just do a direct integration by adding the thing here and then multiplying the bottom by the derivative.